Hey guys, so today what we want to do is continue our discussion from the last several weeks of gases, and we really want to look at a new situation now that we haven't ever dealt with before. Now we want to look at a situation where we have a reaction or a change, and we have a certain number of moles of gas, whatever it might be, and we want to solve for one of the other variables that we can use to describe gases. So we want to be able to look at the temperature of a gas, or the pressure of a gas, or the volume of a gas, okay? So what we want to do is develop some sort of equation that allows us to relate pressure, temperature, volume, and number of moles of a gas in a way that, so if I know three of the variables, I can solve for the other variable, okay, the unknown. So we're going to call this the ideal gas law. So the ideal gas law is just a mathematical relationship that helps us describe gas behavior. So again, this goes back to the assumption we made in chapter 12 that all gases are going to behave as ideal gases. So all these calculations kind of hinge on that. That's why it's called that, okay? So the variables we're going to need to include in this equation are pressure, volume, number of moles, and temperature. Those are the four things that we have used to describe gases thus far. So if we think back to what we know about those topics and those variables, we know that a proportion exists between volume and number of moles. Okay, so volume divided by number of moles, as long as all others are constant, or is a constant, excuse me, as long as pressure and temperature are constant there. And that was Avogadro's law. If you forgot, write that in. We also know a proportion exists between volume and temperature. Okay, so volume divided by temperature for a sample is constant, assuming that pressure and number of moles are the same. That is Charles' law. Then we also remember Gay-Lussac's law that describes the relationship between pressure and temperature. Then finally, we need to look at Boyle's law. Boyle's law tells us there's an inverse relationship between volume and pressure. Okay, so now, if we think about all these and we could combine them together, how could we do that? So, all these things here, all these terms, okay, volume divided by moles, volume divided by temperature, pressure over temperature, pressure times volume, equal a constant value. Okay, so we can use that K that is used to represent constant to combine these four terms together. So I could say that pressure times volume divided by number of moles times temperature equals a constant. So all we did was combine those four things that we already know. And this is what we will call the ideal gas law. Okay? So the ideal gas law tells us that the volume of a gas varies directly with the number of moles and the Kelvin temperature, and inversely with the pressure. Okay? So we already knew those things in individual pieces. Now we just stuck them all together. Okay? And hopefully you could fill in the names for the four laws we just combined there. Okay? But now we want to introduce kind of a new term, not a variable, a new constant. So instead of just calling this K, we're going to use the letter capital R. Okay? So capital R is the symbol that we use for the ideal gas law constant. And a lot of times you'll hear it just called the ideal gas constant. Okay, so the value rather is dependent upon the units for the variables plugged in. Okay, so typically we'll look at R being dependent on the units of pressure. Okay, so there are several units we know: millimeters of mercury, ATM, kPa. So what we need to do is look at how we can figure out what this R value is. Okay, we know that it's a constant, but we don't know what its value is. So what we're going to do is we're going to try and derive the value of R for 1 mole of gas at STP. And the reason we choose to figure out the value of R for 1 mole of gas at STP is because we know some things about that gas. Okay, we know that 1 mole of gas at STP has a volume of 22.4 liters. That allows us to do that calculation there. Okay? So if I plug in the values I know for this up here, I can say R equals PV over NT. So again, I just chose a situation, STP. So standard pressure, I could say 1 atm. I know at STP, 1 mole of gas has a volume of 22.4. But I'm going to use 22.4141 liters. Okay, it's a little more accurate, precise number there. That way my number will have more significance when I finish. So the problem tells me I have 1 mole, or the situation tells me 1 mole of gas. And the temperature is standard temperature and pressure is 273. I want to be a little bit more accurate, 273.15 Kelvin. Okay? So if I type that in the calculator, I get 0.0821. And none of my units cancel. ATM times liters over mole times Kelvin. So this is the number that we will learn and memorize as the ideal gas constant. Okay? So one thing that I don't want you to be confused about, this applies to all situations, okay, not just 1 atmosphere and standard temperature there. We just chose this example to solve for R because this is a situation where we know the volume of that gas. Okay, I could take any sample of gas, and if I could measure the number of moles, the pressure, the volume, and the temperature, if I could plug that in, I would always get this number right here. Okay, we just use the situation to derive this. So this part's not so important. That just shows you where the number came from. This is what's important, the actual value of R we will use in the calculations. One thing that can change, though, there's something else that's equivalent to 1 atm. There's several things that are equivalent to 1 atm. So I could have used, let's say, 101.325 kPa. Okay, so if I did that, what I would do is I would get a completely different number. So if I plug in 101.325 kPa in this example, an equivalent number, I'm going to get 8.314 as my number that comes out. And that's still correct. It just has different units. So the units would be kPa times liter over mole Kelvin. Okay. And as you likely could imagine, there would be a different ideal gas constant, a different value of R that we could use if we plugged in millimeters of mercury. Okay, so the value of R is dependent on what units we select for pressure. So it can be kind of confusing and try and memorize a bunch of these constants. So a better option is just to learn this constant. Okay, 0.0821 atmospheres times liters per mole Kelvin. And then if we have a situation where we have a volume, or excuse me, a pressure in a unit that's not atmospheres, I can always just convert that pressure to atmospheres and it'll all work out. So I would just focus on memorizing that number right there. Okay. So then if I plug in R, if I substitute R up here, I want to rearrange so there's no fraction. And I just have PV equals nRT. Okay. So pressure times volume equals the number of moles times the ideal gas constant times temperature. So now we have a formula that allows us to solve for an unknown variable of a gas. Okay, so if I know the pressure, volume, and temperature of a gas, I can then find the number of moles. If I know the pressure, temperature, and number of moles, I can solve for the volume. Because I'll always know R. R is always going to be the same. Okay, so it's a very powerful equation that we use quite a bit because it does allow us now to look at different amounts of gas, different moles of gas at conditions that are not standard, so they're not at STP. Okay. So if we turn over to the next page in the notes, what we want to do now is we want to take that ideal gas law and kind of take it one step further, okay, the ideal gas formula. So let's kind of write out what we start with. So we know that PV equals nRT. But there are some other qualities of gas that we also would like to be able to describe. Okay? Sometimes we want to talk about the density of a gas. Sometimes we want to discuss the number of moles of a gas. Sometimes we want to discuss the actual mass of a gas. So let's go ahead and try and derive a formula that allows us to use some of these variables. So N, of course, is number of moles. Lowercase m, we'll call the mass of a gas in grams. Capital M is the molar mass from the periodic table of a gas in grams per mole. And then density is is a capital D. And we know that density is equal to mass divided by volume. So I know that I can substitute in the number of moles is equal to a mass divided by a molar mass. So that's how I find a number of moles. So if I give you, let's say, 15 grams of oxygen, that would be my mass. I want to know how many moles I have. You would divide 15 by the molar mass of oxygen. So this statement is true. So I can plug that into this formula up here. So I can say PV equals lowercase m RT divided by big M. Okay. Sorry, my M's aren't super clear there. So that is a new form of the ideal gas law that will be very useful to us. So if you want to go ahead and circle that one or put a box around that one, you can. Because that's another form that allows us to use the mass and molar mass of a gas. So we don't need to know the number of moles. So you might be thinking, well, if we have the molar mass and the mass, couldn't we just find the number of moles and make it easier? Yes, but with this form of the equation, we can solve for the molar mass of a gas. So if we know the pressure, volume, temperature, and the mass of a gas, we can actually use this formula to figure out what the molar mass of the gas is, which could help us find the identity of the gas. Okay? So then I can rearrange that formula and solve for our molar mass. So I can say capital M equals lowercase m RT over PV. Okay? So then I know also that mass right here divided by volume is equal to density. So I could combine that term. So I could say capital M molar mass equals density times the ideal gas constant times temperature divided by pressure. Then just to make it easier, I could solve for D for density. So I can say density equals the molar mass times the pressure times the ideal gas constant times the temperature. Okay. So hopefully you followed that. If not, it's not a huge deal. I just wanted to show you where these equations I'm going to write down come from. Okay, on the previous page I showed you where PV equals nRT comes from. Now I just want to show you where these two other equations we use come from. So now we're going to write down PV equals mRT divided by capital M, then also D equals molar mass times pressure divided by RT. Then also you'll need to know R equals 0.0821, and then hopefully you remember the units there are atmospheres times liters over mole Kelvin. Okay. So this is the big takeaway from this video, is you need to memorize these three formulas and the ideal gas constant R there. Okay. So it might be a little bit confusing now why we need all these different forms and why we even need this formula in general. But just bear with me. In the next videos, when we look at problems, it should become hopefully fairly obvious to you why we need first just PV equals nRT, the ideal gas formula, but then also why we need the form that contains mass and density as well. Okay. So that's all for this video. In the next video, we will look at applying this to some practice calculations.